The universe looks almost smooth when seen from far enough away. Galaxies gather into clusters. Clusters connect through long filaments, and between them lie enormous regions of nearly empty space. Together, they form the cosmic web, so vast that individual galaxies almost disappear inside it. But hidden within that web are patterns far larger than scientists expected. One structure may stretch across billions of light years, reaching through a significant part of the observable universe. If it is truly one connected object, then matter may not become evenly distributed on the scales our models predict. So, how could something this large have formed? And does its existence reveal a problem in our understanding of the universe? Before we begin tonight's journey, subscribe if you want more calm space documentaries like this. Leave a like if you enjoy space mysteries. And here is a question. If you could see the cosmic web from outside the universe, which part would you explore first? Let me know in the comments. I will pin the most creative answer. Tonight, you are watching the Just About Space channel. Talking about the largest structure in the universe shouldn't be possible. From Earth, the Milky Way does not feel small. On a clear night, far from cities, it stretches across the sky as a pale river of light. It appears wide enough to divide the darkness, filled with more stars than the eye can separate. The band seems almost permanent, as though it were part of the sky itself, rather than a structure through which the solar system is moving. Yet the light we see is only a narrow view from inside the galaxy. We are not looking at the Milky Way from the outside. We are buried within its disk, surrounded by stars, gas, dust, and distant clouds that block much of what lies beyond them. The bright band across the night sky is the combined glow of countless stars seen along the plane of the galaxy, where the material is most densely gathered. From this position, the Milky Way can seem like the largest thing that meaningfully surrounds us. The solar system is already difficult to imagine in full. Neptune orbits billions of kilometers from the Sun, and even the region influenced by our star extends much farther into darkness. But the distance from the Sun to the nearest star is thousands of times greater than the width of the planetary system. Beyond that nearest star are more stars, then more again, separated by gaps so large that their light takes years, centuries, or millennia to cross. The Milky Way contains hundreds of billions of them. Its disk stretches roughly 100,000 light-years from side to side. Light, moving fast enough to circle Earth several times in a single second, would need around 100,000 years to cross the galaxy. A human life occupies almost nothing beside that distance. Even the entire history of civilization would appear brief compared with the time required for a beam of light to travel from one edge of the Milky Way to the other. The galaxy is not a flat circle with clearly marked borders. It is a broad, rotating system with spiral arms, streams of stars, clouds of gas, clusters, and a central region packed more densely than the area around the Sun. The solar system lies far from the center, inside a smaller feature called the Orion Arm. Most of the Milky Way is shaped by the combined gravity of stars, gas, and a much larger amount of invisible matter spread through a vast halo. The galaxy behaves as one enormous gravitational system, even though its parts are separated by distances that make ordinary ideas of closeness meaningless. From inside, none of this structure can be seen all at once. Humanity has reconstructed the Milky Way through measurements of distance, motion, brightness, and wavelength. Radio observations trace clouds of hydrogen. Infrared telescopes reveal stars hidden by dust. Spacecraft measure the slight apparent shifts of nearby stars as Earth moves around the Sun. Piece by piece, a map emerges. But even the best map remains incomplete. The far side of the galaxy is difficult to study because the center and dense dust lanes stand in the way. Faint stars disappear into the background. Some regions are too crowded for individual objects to be separated clearly. The Milky Way is therefore both our home and an object we have never seen directly from the outside. Every familiar image of the full galaxy is a reconstruction, an artist's view, or a comparison with other spiral galaxies. No spacecraft has traveled far enough to turn back and photograph the complete shape. To see the Milky Way as one object, an observer would need to move tens of thousands of light-years away from the disk. From that distance, the stars that dominate our night sky would begin to merge. The Sun would disappear almost immediately. It would become one ordinary star among hundreds of billions, too faint to identify without knowing exactly where to look. The constellations would vanish because they are patterns created only from Earth's location. Stars that appear close together in our sky are often separated by enormous distances, and from another viewpoint, their arrangement would change completely. Farther away, individual stars would become impossible to separate. The spiral arms would begin to appear as broad, glowing curves. Dark lanes of dust would cut through the disk. The central bulge would become brighter and more obvious, surrounded by the flatter structure of the galaxy. At this scale, the Milky Way might look calm. The explosions, collapsing stars, orbiting planets, and violent events inside it would be too small to see. Billions of individual systems would blend into one faint shape. Every world, including Earth, would be hidden inside the light. Distance removes detail long before it removes the object itself. At several million light-years, the Milky Way would resemble the galaxies visible through telescopes from Earth. Its spiral form might still be clear, but its individual stars would be difficult or impossible to resolve with ordinary instruments. It would become a bright central region surrounded by dimmer arms. The galaxy would no longer feel like a place. It would feel like an object. This change in perspective is essential, because the largest structures in the universe cannot be understood from the scale of planets or stars. Even a galaxy as large as the Milky Way must be reduced to a point. The nearest large galaxy, Andromeda, lies about 2.5 million light-years away. It is larger than the Milky Way and may contain around 1 trillion stars, yet from Earth, it appears as a faint patch under dark skies. Almost all of those stars merge into one soft glow. If planets orbit many of them, then perhaps trillions of worlds are hidden inside a shape that can be covered by a small part of the hand when held at arm's length. Andromeda is not alone. Around the Milky Way and Andromeda are dozens of smaller galaxies, many of them faint dwarf systems. Together, these galaxies form the Local Group. The name sounds modest, but the structure spans millions of light-years. The Milky Way and Andromeda dominate it through their mass. Smaller galaxies orbit them, move between them, or slowly lose stars through gravitational interaction. The Local Group is not isolated. It belongs to a larger galactic environment, containing more groups and clusters spread across a much wider region. Some galaxies gather into dense systems with hundreds or thousands of members. From within one galaxy, a cluster can seem impossibly large. But from far enough away, the cluster also begins to shrink. Individual galaxies blend into points, and the spaces between them become part of a larger pattern. A cluster may contain thousands of galaxies, each holding billions of stars, yet the cluster itself can occupy only a small knot inside a map of the nearby universe. The scale changes faster than human intuition can follow. A planet becomes part of a star system. A star system becomes part of a galaxy. A galaxy becomes part of a group. Groups and clusters become part of structures extending across hundreds of millions of light-years. At every step, something once considered enormous becomes a small component inside something larger. The process does not stop with galaxy clusters. Clusters are not scattered randomly through space. Some gather along long concentrations of matter. Others lie around the edges of enormous empty regions. When astronomers map the positions of galaxies across large distances, a pattern begins to appear. The universe is not filled evenly with bright points. Galaxies form lines, sheets, and curved structures. Dense knots are connected by narrow bridges. Between them are voids where relatively few galaxies exist. The pattern resembles a web, but this web cannot be seen by looking in one direction. It is a three-dimensional structure spread through space, reconstructed from the distances and positions of enormous numbers of galaxies. Every bright point in the map may represent a galaxy containing billions of stars. The larger the map becomes, the smaller each galaxy appears. Eventually, even the Milky Way would no longer be shown as a spiral. It would become one point among countless others. Nothing about the galaxy itself would have changed. Its stars would still orbit. Planets would continue moving around their suns. Clouds would collapse. Black holes would grow. And life on Earth would continue beneath the same sky. Only the scale of observation would be different. From the scale of the cosmic web, the Milky Way is almost invisible. It is not large enough to define the pattern around it. It is carried inside a flow of galaxies shaped by gravity across distances so vast that the entire galactic disk becomes negligible. The local group becomes only a small concentration. Larger clusters become knots. The spaces between them become enormous dark cavities, some stretching across hundreds of millions of light years. No planet can see the full pattern from its surface. The cosmic web is too large for any local observer to view directly. Its filaments extend beyond the distance light can cross during entire civilizations. Astronomers can only build the picture by combining many observations. Each survey adds another section. One map may trace nearby galaxies. Another reaches farther into the past. Radio telescopes reveal gas. X-ray observations show hot material inside clusters. Gravitational lensing exposes mass that produces little or no light. Together, these measurements reveal that the visible galaxies are only part of the structure. Much of the gravity comes from dark matter. Dark matter does not shine, reflect, or absorb light in the ordinary way. It is known through its gravitational effect on galaxies, clusters, and the movement of matter. Without it, the cosmic web would not form in the same way. In the early universe, dark matter began gathering into regions slightly denser than their surroundings. Ordinary matter followed those gravitational wells, eventually forming gas clouds, stars, galaxies, and clusters. The glowing universe grew inside an invisible framework. Every galaxy is therefore part of a structure that extends beyond what the eye can see. The Milky Way is held inside its own dark matter halo, but that halo is also part of a wider distribution connecting groups and clusters across space. The galaxy is not floating alone in emptiness. It belongs to a landscape shaped by matter on scales far beyond its own boundaries. This realization changes the meaning of large. The Milky Way is enormous compared with Earth, yet it is only one luminous piece inside a framework stretching across billions of light years. Andromeda, galaxy clusters, and even superclusters become details within the same pattern. The largest structures are not single solid objects. They are arrangements of galaxies and matter linked through gravity, sometimes spread across distances so great that one side can never influence the other in any simple, immediate way. A wall of galaxies is not a wall like stone. It has no continuous surface. It is a region where galaxies appear more densely concentrated than in the space around them, forming a broad shape inside the cosmic web. The emptiness between its galaxies can still be millions of light years wide. Yet, when viewed from a great enough distance, those separated galaxies outline one enormous structure. This is where the mystery begins. If the universe becomes broadly uniform on the largest scales, then there should be a point at which these walls, filaments, and clusters blend into an even distribution. No region should remain special forever, but some observed patterns appear so large that they approach, or perhaps challenge, the scale where that smoothness is expected. To understand why that matters, the Milky Way must first disappear from view. It must become one point, then part of a knot, then part of a filament stretching through a universe that no single observer can see in full. Only from that scale does the hidden architecture begin to emerge. And once even an entire galaxy had become almost invisible, the darkness around it could begin revealing the vast web that holds galaxies together across the universe. At the scale of the cosmic web, a galaxy is no longer the main subject. It becomes a marker, one bright point, tracing a structure far larger than itself. The pattern is not obvious in ordinary photographs. A deep image of the sky may contain thousands of galaxies, but they are projected onto a flat surface. Some are nearby, others are billions of light years farther away. Their true arrangement is hidden until distance is added. Astronomers build three-dimensional maps by measuring how the light from each galaxy has been stretched during its journey to Earth. The greater the stretching caused by cosmic expansion, the more distant the galaxy is likely to be. When enough galaxies are placed into space, the distribution stops looking random. Dense concentrations appear. Long lines emerge between them. Wide sheets of galaxies curve through the map, and between those regions lie enormous spaces containing very little visible matter. This is the cosmic web. It is the largest known pattern in the distribution of matter. The name can make it sound thin and delicate, but its filaments can contain thousands of galaxies and extend across hundreds of millions of light years. Their width alone may exceed the size of many galaxy clusters. Where several filaments meet, matter gathers into dense knots. These knots can become galaxy clusters, among the most massive gravitationally bound structures in the universe. A single rich cluster may contain hundreds or thousands of galaxies, surrounded by hot gas and held inside an enormous concentration of dark matter. They move through the cluster at high speeds, passing one another across distances that still remain enormous. Their stars rarely collide directly, but the galaxies can pull on one another, lose gas, change shape, and merge over time. Between the clusters, filaments form the bridges. Some contain groups of galaxies. Others are filled mainly with thin gas and dark matter, with only a small number of bright objects revealing their path. It can be too cool for strong X-ray emission and too hot to remain visible in ordinary light. Astronomers detect it indirectly through absorption in the light of distant objects, or through the way gravity bends background images. The web is therefore more massive than its visible galaxies suggest. The stars are only the brightest part of a structure made largely from material that does not shine. Dark matter provides most of the gravity. It does not form stars or glowing clouds, yet it creates the framework into which ordinary matter falls. Galaxies gather where dark matter is concentrated, tracing an invisible landscape that began forming long before the universe reached its present appearance. A filament can continue through space, even where few galaxies are visible. A cluster may be surrounded by a dark matter halo, extending far beyond the light. Empty-looking regions may contain thin material too faint to detect easily. The true structure is deeper than the map. On the other side of the web are the voids. These are not completely empty spaces. They contain scattered galaxies, thin gas, dark matter, and radiation. But compared with the filaments and clusters around them, their density is extremely low. Galaxies gather around the boundary while the interior remains relatively empty. As the universe evolves, gravity slowly draws matter away from the underdense center and toward the denser structures outside. This movement helps shape the web. Filaments do not grow in isolation. They are also defined by the empty spaces pressing between them, separating one concentration of matter from another. The universe is structured as much by absence as by presence. The web is three-dimensional, irregular, and constantly changing. Filaments can bend, divide, and merge. Clusters grow where matter continues flowing inward. Voids widen as the universe expands. There is no fixed grid beneath it. Every part of the pattern emerged from gravity acting on an uneven distribution of matter. The scales involved are difficult to hold together. A galaxy cluster may span several million light-years. The filaments connecting clusters can extend 100 times farther. A supercluster can include many clusters and groups spread across a region so large that not all of it is gravitationally bound. The word structure can therefore be misleading. A cosmic structure may be defined more loosely. It can be a recognizable concentration of galaxies without behaving as one solid object. Its distant regions may never exchange information quickly enough to act as a single system. Gravity travels at the speed of light. A disturbance on one side may require hundreds of millions of years to affect another region, and the expansion of the universe may prevent some connections from strengthening at all. The pattern can exist without being unified in the ordinary sense. This becomes important when astronomers speak about the largest structures ever found. A long concentration of galaxies may look connected in a map, but appearance alone does not prove that every part belongs to one physical object. Several separate filaments may align along the same direction. A sparse sample may leave gaps that are filled by expectation. A broad region can appear continuous, even if it contains multiple independent structures. A cluster belongs to a filament. A filament may belong to a wall. Several walls may outline a void. From a greater distance, these features may blend into something larger. Where one structure ends and another begins is not always clear. Astronomers must choose density thresholds. They decide how closely galaxies must be spaced before they are treated as part of the same feature. Changing that threshold can divide one large structure into several smaller ones or join neighboring structures together. This does not mean the structures are imaginary. The concentrations are real, but their names and boundaries are interpretations of a continuous field. Its visible disk has no perfectly sharp edge. Stars become gradually less common farther from the center. The dark matter halo extends beyond the bright galaxy. Streams and dwarf galaxies blur the boundary between the Milky Way and the space around it. At the scale of the cosmic web, this uncertainty becomes much greater. A wall can stretch across such a wide distance that only parts of it are mapped clearly. Faint galaxies may be missing. Dust, survey limits, and the direction of observation can alter the apparent pattern. A nearby filament can be studied through many galaxies with well-measured distances. Its shape may be reconstructed in detail. A structure billions of light-years away may be inferred from a far smaller number of bright events or galaxies. The farther the structure, the earlier the universe we are seeing. A filament seen 1 billion light-years away is seen 1 billion years in the past. A far more distant wall may be seen as it existed when the universe was much younger. The nearby web reveals a mature universe filled with large clusters and older galaxies. Deeper surveys show earlier stages, when structures were smaller, denser, and still assembling. By looking farther away, astronomers watch the web grow backward toward its origin. There was a time when no galaxy clusters filled the knots. No long walls had reached their present forms, and no giant voids had opened between them. The cosmic microwave background preserves a faint image of this earlier state. It comes from a time when the universe had cooled enough for light to travel freely, long before stars and galaxies formed. Across that ancient glow are tiny temperature differences, revealing regions that contain slightly more or slightly less matter than average. Yet they became the seeds of everything seen in the cosmic web today. Slightly denser regions attracted more matter. Slightly emptier regions lost matter to their surroundings. Over billions of years, those small variations grew into clusters, filaments, walls, and voids. The present universe contains black holes, galaxies, clusters, and empty regions separated by enormous differences in density. Gravity transformed subtle unevenness into structure. Cosmic expansion continually increased the distances between unbound regions. Dark matter gathered early, and created deep gravitational wells. Gas fell into those wells, heated, cooled, and formed stars. The cosmic web became the result of several processes operating across different scales. The web continues changing now. Galaxy clusters still absorb smaller groups. Filaments continue directing matter toward dense knots. Voids continue growing. Distant regions move apart as the expansion of the universe accelerates. Others will break apart, in a practical sense, as their components lose contact across expanding space. Over immense time, galaxies outside our local gravitational region may move beyond visibility. Their light will become more stretched and faint until future observers can no longer detect them. A civilization living in the far future may see only the galaxies gravitationally bound to its local region. Humanity lives during an unusual period when distant galaxies remain visible and the large-scale pattern can still be reconstructed. A telescope can observe only a limited area, detect objects above a certain brightness, and measure distances with limited precision. Faint galaxies fall below the threshold. Dust hides some regions. Instrumental limits create gaps. A pattern may be real, exaggerated, or partly shaped by the way the survey was designed. The largest features demand the greatest caution because their full size may approach the size of the map itself. If a wall extends almost from one side of a survey to the other, it may continue beyond the observed region. Or it may appear unusually large because the survey captured only one direction of a more complex network. Astronomers compare observations with simulations to test these possibilities. A simulation begins with conditions resembling the early universe. Dark matter and ordinary matter evolve under gravity and expansion. Over time, a synthetic cosmic web forms. Researchers ask how often structures of a given size appear. They test whether enormous walls are expected, rare, or inconsistent with the model. Even patterns that seem extraordinary may appear somewhere inside a sufficiently large simulated volume. But a structure can become so large that it raises a more serious question. At sufficiently great scales, the universe is expected to become statistically uniform. Clusters and voids should average together. No direction should remain permanently denser than another. The web should fade into smoothness when viewed across a large enough volume. It means the differences should become smaller as the scale increases. A small map may show one cluster and one void. A larger map contains many of both. Their effects begin to balance. At some scale, no single wall or empty region should dominate the entire picture. Yet the cosmic web does not make that transition obvious. Its largest walls and filaments appear to continue across astonishing distances. Some accepted structures stretch over 1 billion light-years. The problem is whether they remain coherent enough to be considered one structure at scales, where the universe should already look broadly even. A newly discovered object, larger than an older one, may be interesting. A structure large enough to challenge the expected smoothness of the universe touches the model used to explain the entire cosmic history. The question then becomes more than how far the structure extends. Astronomers must ask whether it is truly connected, whether the evidence is strong, whether the survey is biased, and whether the expected scale of uniformity has been understood correctly. Its form follows gravity, yet it contains accidents of history. It approaches smoothness on large scales, yet local patterns can remain enormous. A wall may be statistically allowed while still appearing almost impossible from a human perspective. Before deciding that any one discovery breaks cosmology, the process that built the web must be followed back to the beginning. The long filaments, dense clusters, and hollow voids all grew from differences that were once almost too small to measure. It emerged slowly as gravity amplified the earliest imperfections in matter. And once the cosmic web had revealed its filaments, knots, and enormous voids, the deeper question became how gravity could have built such a vast architecture from a universe that began almost smooth. The early universe was hot, dense, and filled with matter and radiation. On the largest scales, it was remarkably uniform. No galaxy clusters had formed. No voids had opened. No long walls of galaxies crossed the darkness. But the universe was not perfectly smooth. Tiny differences existed from one region to another. Some places contained slightly more matter than average. Others contained slightly less. The contrast was extremely small, yet gravity did not need more. A region with a little extra matter produced a little extra gravitational pull. Nearby material began moving toward it. As more matter gathered, the pull strengthened, drawing in even more. Across billions of years, this simple imbalance transformed an almost smooth universe into the cosmic web. The oldest visible trace of those differences remains in the cosmic microwave background. This light was released when the universe had cooled enough for atoms to form. Roughly 380,000 years after the beginning, the universe behaved like a glowing fog. Photons repeatedly scattered from charged particles. When electrons joined atomic nuclei, the fog cleared, and the trapped radiation began moving across space. Cosmic expansion has stretched it into microwaves, but precise measurements reveal tiny temperature differences across the sky. Those variations mark regions that were slightly denser or slightly emptier than others. The early universe, seen in this light, appears almost uniform. The difference between one region and another may be only a few parts in 100,000. From those faint imperfections, gravity eventually created clusters containing thousands of galaxies and voids stretching across hundreds of millions of light years. Gravity works across enormous distances, but it does not instantly organize the universe. Matter responds locally to the uneven gravitational field around it. Matter falls inward from several directions. Collapse does not happen equally along every axis, so broad regions can flatten into sheets. Those sheets can narrow into filaments, and the filaments can feed dense knots. A broad region becomes a sheet. The sheet narrows into a filament. Several filaments meet at a cluster. Matter leaves regions that began slightly less dense and flows toward nearby concentrations. As the universe expands, these underdense regions widen. Their interiors become emptier, while their edges become more sharply defined by surrounding filaments and walls. But ordinary matter could not have built this architecture alone. In the early universe, normal matter was strongly affected by radiation. Pressure resisted collapse, and charged particles remained coupled to light. It did not scatter light in the same way, so it could begin gathering under gravity while ordinary matter was still trapped inside the hot early plasma. Long before stars appeared, it began forming a hidden network of denser regions. After atoms formed and radiation could travel freely, ordinary gas fell into those gravitational wells. Where dark matter gathered, gas became denser. Dense gas cooled more effectively. Clouds collapsed, and the earliest stars ignited. They were not calm spirals like the Milky Way. They were younger, more compact, and often irregular. Many collided and merged, creating larger galaxies over time. Small dark matter halos merged into larger halos. Galaxies entered groups. Groups fell toward clusters. Filaments carried matter toward the densest intersections of the web. Small structures appeared earlier. Larger structures assembled later from the movement and merging of smaller ones. Galaxy clusters still gained new members. Galaxies continued drifting along filaments. Dark matter halos merge, while gas is heated, compressed, and sometimes stripped away. A galaxy may travel along a filament toward a cluster for billions of years. As it enters the denser region, its gas can be disturbed. Encounters with other galaxies become more likely. Star formation may increase, weaken, or stop. A galaxy inside a quiet filament may develop differently from one deep inside a crowded cluster. A galaxy inside a void may experience fewer mergers and receive less fresh gas. A planet forms around a star. The star belongs to a galaxy. The galaxy occupies a location inside the cosmic web. Tiny density variations became dark matter halos. Halos gathered gas. Gas formed galaxies. Galaxies formed stars. Stars formed planets. The same ancient irregularity that shaped the cosmic web eventually helped create the conditions in which life could appear. Without denser regions, matter might not have collapsed into galaxies at all. There would have been no stars to create heavy elements, no planets, and no observers looking back toward the beginning. The answer may reach into the earliest fraction of a second. Many cosmological models describe a brief period of extremely rapid expansion, called inflation. During this stage, tiny quantum variations may have been stretched to enormous scales. A fluctuation once far smaller than an atom could become the seed of a future galaxy cluster. The idea connects the smallest known behavior of nature with the largest structures in existence. The details remain uncertain, but the pattern seen in the cosmic microwave background supports the idea that the early universe contained variations across many scales. The structure of the present universe carries a faint memory of that beginning. The exact location of every galaxy cannot be predicted from one simple map. Too many mergers, collisions, and local events change the details. But the broad, statistical pattern remains connected to the starting conditions. The sizes of clusters, the spacing of filaments, and the distribution of voids all preserve information about the early universe. It shows what gravity has built, while retaining traces of what existed before stars appeared. Astronomers use this pattern to test models of the universe. If there were more dark matter, structure would grow differently. If cosmic expansion followed another history, clusters and voids would reach different sizes. If the original variations had another strength, the present web would not look the same. Computer simulations allow these possibilities to be tested. A simulated universe begins with an almost smooth distribution of matter based on observations of the early cosmos. Gravity is then allowed to operate while space expands. At the beginning, very little appears to happen. Small ripples become stronger. Dense regions begin gathering matter. Empty regions begin losing it. As simulated time advances, filaments emerge. They connect growing halos. Knots become clusters. Voids open between the denser structures. The final result often resembles the observed universe with remarkable detail. The web is not drawn into the simulation by hand. It appears naturally when gravity, dark matter, ordinary matter, and expansion evolve from the measured early conditions. This is one of the strongest reasons scientists trust the general model. But the match is not perfect. Simulations cannot follow every particle in the observable universe. They divide space into manageable sections and approximate complicated events inside galaxies. Star formation, supernovae, black holes, magnetic fields, and radiation can all change the behavior of ordinary matter. Dark matter is easier to model because it interacts mainly through gravity, yet its true identity remains unknown. The model can describe how dark matter behaves without revealing what it is. This creates a strange situation. Most of the material shaping the cosmic web has never been directly identified in a laboratory. Its gravitational influence is visible everywhere. It surrounds galaxies, holds clusters together, bends light, and guides the formation of the largest structures. The web is built upon something invisible. Gravity itself also behaves differently at these scales from the simple picture of a planet orbiting a star. There is no single center of the cosmic web. Matter responds to the combined gravitational landscape around it. A cluster pulls nearby galaxies inward. A filament guides movement along its length. A void affects motion because it contains less mass than the regions around it. Galaxies tend to move away from emptier regions and toward denser ones, not because voids push them, but because gravity pulls more strongly elsewhere. From a large enough view, matter appears to stream through the universe. Some galaxies move at hundreds or thousands of kilometers per second. Even at those speeds, crossing a large filament can require billions of years. The web changes too slowly for human eyes. Maps show fixed lines and knots, but they represent motion unfolding across cosmic time. Expansion adds another layer. Gravity gathers matter where it can, while cosmic expansion increases the distance between regions that are not strongly bound. Inside galaxies and clusters, gravity dominates. Across larger distances, expansion can carry structures apart. A supercluster may look like one immense object, even though much of it is not bound strongly enough to collapse together. Its galaxies can share a broad pattern without moving toward one common center. This helps explain how structures can extend across enormous distances without behaving like solid objects. Gravity did not assemble the cosmic web from one side to the other. It acted everywhere at once. Each region responded to nearby differences in density. The global pattern emerged from countless local movements happening throughout space. No signal crossed the entire web to direct its shape. The architecture appeared because the same physical laws operated everywhere on an initial pattern, already containing variations across different scales. This distinction becomes important when a structure appears billions of light-years long. A long chain of galaxies may share a statistical origin without acting as one gravitationally bound object. Several filaments may align into a broad wall. Neighboring concentrations may look connected, even when their distant sections have little physical influence on one another. The word structure does not always mean one unified body. It can mean a recognizable pattern in the distribution of matter. The Standard Model predicts both order and chance. It predicts filaments, clusters, and voids, but it also allows unusually large arrangements to appear inside a universe containing an enormous number of regions. Rare does not mean impossible. A structure with a very low probability may still appear somewhere if the observable volume is large enough. Record holders are expected to be unusual, but there should still be limits. Gravity has had only a finite amount of time to act. Signals travel at a finite speed. Expansion separates distant regions. The original density variations had measured strengths. Together, these conditions restrict how much structure can grow and how coherent it can become. The cosmic web can be vast without being unlimited. At sufficiently large scales, clusters, voids, and walls should begin averaging together. The universe should become statistically uniform, even though smaller regions remain highly uneven. The difficulty is deciding where that transition occurs. A structure hundreds of millions of light-years wide may be completely consistent with the expected web. A structure extending across several billion light-years may be harder to interpret. Astronomers must ask whether it is truly one object, several aligned features, a statistical accident, or a sign that the expected scale of smoothness has been estimated incorrectly. Before the most extreme claims appeared, earlier surveys had already discovered walls large enough to transform how the universe was pictured. Each new map extended the known architecture farther. Clusters became parts of superclusters. Superclusters became sections of walls. Voids became enormous regions bounded by galaxies. The cosmic web was revealed through structures that once seemed almost too large to exist. And once gravity had transformed tiny ancient imperfections into the cosmic web, the only way to understand our place inside it was to locate the Milky Way within the larger flows, clusters, and structures surrounding us. The solar system does not sit near the center of the Milky Way, and the Milky Way does not sit near the center of the universe. There is no known central point around which all galaxies are arranged. The cosmic web has no single middle, no privileged direction, and no place from which its full shape becomes simple. Our position can only be described through relationships. The Sun belongs to the Milky Way. The Milky Way belongs to the local group. The local group moves inside a much larger landscape of galaxies, clusters, filaments, and voids. Each layer gives Earth another address, though none has a perfectly sharp border. The local group contains the Milky Way, Andromeda, the Triangulum Galaxy, and many smaller galaxies. Some of the smaller systems orbit the two largest members. Others move slowly through the space between them, responding to the combined gravity of the group. The Milky Way and Andromeda are approaching one another. Their collision lies several billion years in the future, yet gravity has already placed them on a shared path. When the galaxies finally meet, most stars will pass without direct collision, because the spaces between them are enormous. The galaxies themselves will not remain unchanged. Their shapes will stretch and distort. Streams of stars may be thrown outward. Gas clouds may be compressed, and new stars may form as the two systems gradually merge. The local group is therefore not a quiet collection frozen in space. It is a small gravitational system still evolving. From farther away, however, even this group becomes difficult to notice. The Milky Way and Andromeda dominate our local view, but together they form only one small concentration among many others in the surrounding universe. Roughly 50 million light-years away lies the Virgo cluster, a far denser gathering of galaxies. It contains hundreds, perhaps thousands of members and far more mass than the local group. For many years, astronomers described our wider surroundings through the Virgo supercluster, a broad region containing the local group, the Virgo cluster, and many neighboring groups. The word supercluster can make the structure sound like one enormous object held together as tightly as a galaxy cluster. The reality is less simple. Some nearby galaxies move toward Virgo. Others respond more strongly to different concentrations. Cosmic expansion separates many regions, even while local gravity pulls certain systems together. The larger environment is better understood through motion. Galaxies do not merely show where matter is located. Their movement reveals where gravity is drawing them. A galaxy carried only by cosmic expansion would move away in a predictable way. But many galaxies have additional motion caused by the unequal distribution of matter around them. The Milky Way shares this wider flow. Our galaxy, the local group, and many nearby systems move through the cosmic web under the influence of structures far beyond the local group itself. One important region became known as the Great Attractor. The name suggests one hidden object, but the Great Attractor is not a single black hole or unseen galaxy. It is a broad concentration of clusters, galaxies, and dark matter whose combined gravity affects motion across a vast area. Part of it lies behind the plane of the Milky Way. Stars and dust inside our own galaxy block visible light from that direction, making the surrounding web harder to map. Infrared, radio, and X-ray observations reveal more of what is hidden. They show that the Great Attractor belongs to a larger gravitational landscape rather than standing alone. Farther away lies the Shapley concentration, another enormous gathering of galaxy clusters whose mass also influences nearby cosmic flows. The local group is not falling toward one simple destination. It responds to several dense regions and to the emptiness of nearby voids. A large underdense area known as the local void lies close to our galactic neighborhood. Because it contains less matter, gravity pulls more strongly from the denser regions on the opposite side. The local group therefore appears to move partly away from emptiness and partly toward concentration. This is the cosmic web experienced from within. There is no glowing filament crossing the night sky. The structure reveals itself through the positions of galaxies, the distances between them, and motions accumulated over millions of years. Earth moves around the Sun. The Sun orbits the Milky Way. The Milky Way moves within the local group. The local group moves through the larger distribution of matter. All of these motions occur at the same time. Nothing nearby feels the journey because everything around us shares it. The night sky appears calm while the entire galaxy travels through the web. By measuring the motions of many nearby galaxies, astronomers reconstructed a larger region of shared gravitational flow. They named it Laniakea, often translated as immense heaven. Laniakea contains the Milky Way and roughly 100,000 other galaxies spread across a region hundreds of millions of light-years wide. Its shape is defined not only by where galaxies appear, but by the directions in which they move. The galaxies flow through gravity much as streams follow the slopes of a landscape. There is no solid ground beneath this comparison. The slopes are created by mass. The streams are galaxies. The valleys are gravitational basins formed by visible matter and dark matter together. The Milky Way occupies a distant outer part of this immense structure. Laniakea does not have a bright edge. Its boundary is placed where the direction of galactic flow changes. On one side, galaxies move toward one gravitational basin. Beyond it, they move toward another. That border is uncertain and can shift as measurements improve. Hidden matter may change the inferred flow. New galaxy distances may redraw part of the map. Cosmic expansion may eventually separate regions that appear related today. Laniakea is therefore a useful description of motion, not a permanent solid object. Not all of its galaxies are bound strongly enough to collapse into one future system. Some parts will continue moving apart. This difference matters at the largest scales. A galaxy cluster can remain gravitationally bound. Its galaxies may orbit, interact, and eventually merge. A supercluster often describes a wider pattern. Its distant parts can share a common structure without sharing one final destination. Once a cosmic feature receives a name, it is easy to imagine that nature has drawn a border around it. But the web is continuous. Laniakea connects to neighboring filaments and sheets. Galaxy concentrations fade into other concentrations. Matter does not stop where one catalog ends. Nearby lies the Perseus-Pisces supercluster, a long chain of galaxies and clusters forming, one of the most striking structures in the local universe. Other filaments extend toward Coma, Hercules, and regions beyond the depth of nearby maps. From a sufficiently distant view, Laniakea becomes one feature among many. Its 100,000 galaxies compress into a small region inside a map spanning billions of light-years. The name Immense Heaven begins to feel strangely local. This repeated loss of scale defines the journey outward. Earth seems large until compared with the Sun. The Sun becomes small inside the Milky Way. The Milky Way becomes one galaxy inside Laniakea. Then, Laniakea becomes a modest concentration inside the broader cosmic web. There is always another scale at which the previous structure begins to disappear. But locating the Milky Way is not only an exercise in making it seem small. Its position gives astronomers a starting point from which to understand how matter flows through the nearby universe. The local group, Virgo cluster, Great Attractor, Shapley concentration, local void, and Laniakea belong to one connected picture. Together, they show that galaxies are not scattered randomly. Their positions and motions follow the gravitational landscape of the cosmic web. The map remains incomplete. The Milky Way hides part of the nearby universe behind its disk. Galaxy distances contain uncertainty. Dark matter contributes gravity without producing light. Even the boundary of Laniakea depends on the available observations. Future surveys may redraw our cosmic address. The Milky Way will not move to a different location, but the way humanity describes that location may change. This has already happened. The local group was once treated mainly as a collection of nearby galaxies. Later, it was placed inside the Virgo supercluster. Motion-based maps then placed it within Laniakea. Each description revealed another layer without erasing the earlier ones. Larger surveys may show that these names capture only portions of a more complicated flow. The universe does not grow when a new structure is discovered. Human knowledge expands into what was already there. The same change occurred as galaxy surveys reached beyond the local universe. Early maps contained too few galaxies to reveal the full pattern. They showed isolated groups and clusters separated by large, uncertain spaces. As surveys became deeper and wider, galaxies began forming unexpected shapes across the maps. Long arcs emerged. Dense bands crossed regions once assumed to be more evenly filled. Clusters that appeared separate became connected through broad concentrations of galaxies. Some of these features extended far beyond the superclusters used to describe our local surroundings. They became known as galaxy walls. A galaxy wall is not solid. It is a vast sheet or concentration where galaxies gather along part of the cosmic web. Its thickness may contain clusters, groups, and smaller filaments. Its length can stretch across hundreds of millions or more than 1 billion light-years. The spaces between its galaxies remain enormous. Yet, from a distant view, those scattered systems outline one broad feature. No observer inside a single galaxy can see the whole wall directly. It must be reconstructed from thousands or millions of measured positions. Distance errors can blur its shape. Survey boundaries can hide its continuation. Missing galaxies can create gaps that are difficult to interpret. Even so, the earliest large walls changed the way the universe was pictured. The web was no longer only a pattern predicted by gravity and computer simulations. It was appearing in real surveys drawn by galaxies across enormous regions of space. Some walls fit comfortably within the expected cosmic structure. Others appeared unusually long. Each discovery pushed the known scale farther and made the local superclusters seem smaller. The search for the largest structure did not begin with a pattern billions of light-years across. It began by mapping our own surroundings, following the motion of nearby galaxies, and realizing that the local group, Virgo and Laniakea, were only small pieces within a much larger network. And once our place inside the local cosmic flows had been mapped, the same surveys began revealing walls of galaxies so vast that even superclusters became only smaller sections within them. No telescope could point toward the sky and capture an entire galaxy wall in one image. The structures were too large, too faint, and too deeply spread through three-dimensional space. For most of human history, the night sky offered only direction. A star or galaxy could be placed on a map of the heavens, but its distance remained uncertain. Nearby galaxies and faraway galaxies could appear beside one another even when enormous stretches of space separated them. A dense-looking patch might be a true cluster, or it might be a chance alignment of objects at different depths. The hidden structure could only emerge when astronomers learned to measure the motion of galaxies through their light. Most galaxies show a shift toward the red end of the spectrum. Their light waves have been stretched as the universe expands, and the amount of that stretching provides a way to estimate distance. Galaxies also move because of local gravity, and those motions can slightly alter the measured redshift. But across large surveys, the pattern becomes reliable enough to build a three-dimensional map. Thousands of separate points begin occupying a volume rather than a flat sky. Measuring a galaxy's spectrum required time, and each observation added only one more distance. A survey could not collect millions of galaxies as modern projects now can. Astronomers therefore selected thin slices of the sky. The slices were narrow in one direction, but extended outward through space, creating maps shaped like wedges. Earth sat at the narrow point, while measured galaxies spread outward with increasing distance. Galaxies gathered into long bands, surrounding dark, empty regions. Dense clusters were linked by thinner bridges. Instead of a smooth distribution, the maps showed something closer to bubbles, sheets, and branching lines. One of the most influential surveys was carried out by astronomers at the Center for Astrophysics. By measuring redshifts for thousands of galaxies, the team created maps of the nearby universe with enough detail to reveal a feature that crossed much of the observed region. The name was direct because the map made it difficult to describe in any other simple way. Galaxies seemed to form a broad sheet stretching through space, with clusters embedded along it and large voids lying beside it. Its galaxies remained separated by millions of light years. Smaller groups, clusters, filaments, and empty spaces existed inside the larger feature. Yet across the survey, these pieces followed the same extended region. The minimum measured length was hundreds of millions of light years. Its full shape reached beyond parts of the available map, which meant the survey itself limited the estimate. The largest feature did not appear comfortably contained inside the observation. Astronomers could say where the measured part ended, but not necessarily where the real structure ended. From Earth, the Great Wall could not be seen as one glowing object. It crossed different directions and distances, hidden among countless foreground and background galaxies. In reality, its thickness alone contained enough space for entire clusters and millions of planetary systems. Its length was close to 500 million light-years by commonly used estimates. Light leaving one end, when complex life on Earth was only beginning to spread through the oceans, would still not have reached the other end today. The Milky Way could be placed across that distance thousands of times. Even Laniakea, our immense local supercluster, would no longer dominate the map. The Great Wall showed that a named structure could contain many systems already described as enormous. Before broad redshift surveys, galaxies were often discussed mainly as individuals, groups, and clusters. The Great Wall made the larger arrangement difficult to ignore. They could belong to long connected sheets extending across a major part of the nearby universe. The dark regions beside the wall were not small gaps between galaxies. They were enormous underdense spaces whose boundaries helped define the wall itself. The map looked as though matter had gathered around the surfaces of vast empty bubbles. If each deeper survey revealed structures as large as the survey itself, how could astronomers know when they had reached a scale where the universe became broadly uniform? A larger map should contain many walls and voids, allowing their differences to average together. The Great Wall made the required map much larger than expected. Was this wall a normal part of the cosmic web, or had the survey happened to pass through an exceptionally rich region? A rare structure can appear especially important when it crosses the exact region being measured. Later observations filled in more of the surrounding volume. Simulations produced sheet-like structures, filaments, and voids from the growth of dark matter. It became an extreme but understandable part of a web shaped by gravity. Still, it remained a reminder that the universe could organize matter across distances far beyond individual superclusters. Technology improved. Telescopes could collect the light of many galaxies during one observing session. Automated systems measured spectra, processed redshifts, and added them to enormous databases. The Sloan Digital Sky Survey changed the depth and width of the map. Instead of several thousand galaxy distances, astronomers could work with populations reaching into the hundreds of thousands and beyond. Thin wedges became broader volumes. Individual clusters appeared inside filaments. Voids gained more complete boundaries. Features that had looked isolated could be connected across wider regions. The structure stretched roughly 1.37 billion light-years across the mapped universe. That made it around 80% longer than the earlier Great Wall, according to the measurement used in its original description. It had moved into a scale measured in more than 1 billion light-years. A beam of light could leave one side long before complex animals existed on Earth, and still be traveling toward the other side today. Thousands of Milky Ways could fit along its length with room remaining between them. Yet the wall itself was composed of galaxies that appeared as individual survey points. The map compressed enormous clusters, billions of stars, and uncounted planetary systems into a narrow band. Later studies revealed a complicated region containing several superclusters with different internal shapes. Some parts resembled rich filaments. Others formed branching systems with several dense centers connected by chains of galaxies. The wall was less like one smooth sheet, and more like a large arrangement of neighboring structures. Calling it one wall was useful for describing the broad concentration, but it did not mean the entire feature behaved as one gravitationally bound body. Some clusters were still assembling, groups were falling inward, dense cores contained old galaxies, while outer regions continued changing. The feature was one pattern, but not necessarily one object in the everyday sense. A billion light-year wall is too extended to behave like one solid system with a shared center. Its identity comes from the way galaxies are distributed across the cosmic web. Its exact boundary depends on how that concentration is measured. Astronomers can smooth the galaxy distribution into a density field. Regions above a chosen density can be joined into superclusters and walls. A slightly different threshold may connect two neighboring sections or separate them. The record can therefore depend partly on definition. The galaxies are present, and the broad concentration is visible in the data. But it warns against treating every named wall as though nature had marked its edges. One structure fades into another through bridges, thinner filaments, and lower density regions. Human analysis divides that landscape into objects so they can be compared. Could a universe beginning with tiny density variations naturally produce something resembling the Sloan Great Wall? Some early discussions made the structure sound deeply threatening to the Standard Model. A feature more than 1 billion light-years long seemed uncomfortably large beside the expected transition toward cosmic smoothness. But length alone does not determine whether a structure violates that expectation. A long, narrow feature can cross a large distance while occupying only a small fraction of the surrounding volume. Several connected superclusters can create a dramatic outline without producing a density imbalance across the entire universe. Simulations of large volumes can contain rare walls and unusually extended arrangements. The question is not whether the map contains a long line, it is how dense, coherent, and statistically unlikely the full structure is. The observable universe gives rare patterns many chances to appear. If billions of regions are examined, one of them will naturally become the largest known example. The Sloan Great Wall therefore became both a discovery and a lesson in caution. It showed that the cosmic web can create structures far larger than the first surveys revealed. It also showed why the word largest cannot be separated from the method used to identify the structure. A new survey may join more regions together. A deeper survey may reveal that apparent gaps contain faint galaxies. A different statistical method may divide the same wall into several superclusters. The universe remains the same while the catalog changes. A wall hundreds of millions or billions of light-years long is not observed at one shared moment. Light from its nearer sections began traveling later than light from its farther sections. The map places them together as though they form one present structure, but each part is seen at a different age. The Sloan Great Wall is seen through light that left its galaxies roughly 1 billion years ago. Those galaxies have continued evolving during the time their light traveled toward Earth. Clusters have gathered new members, galaxies have merged, stars have formed and died. It is a pattern reconstructed from delayed light, uncertain distances, selected galaxies, and chosen boundaries. Gravity created extended regions where galaxies became more common, separated by voids, where they became rare. The CFA Great Wall and the Sloan Great Wall revealed this structure at two different levels. One emerged when thousands of redshifts transformed the nearby universe into a wedge-shaped map. The other emerged when a much larger digital survey carried the same method deeper and wider. The early wall reached the edge of the map because the map was still small. The Sloan Wall appeared inside a broader survey, but its great length showed that even the expanded view had not exhausted the scale of cosmic structure. As observations improved, the largest known structures continued growing. This could be partly expected. A larger volume has a better chance of containing a rarer and more extended feature. Would each new map reveal another wall close to the size of the survey? Would the universe ever settle into the smooth average required by cosmology? Or were astronomers joining separate parts of the web into structures that appeared larger than they physically were? Researchers needed better maps, clearer definitions, and comparisons with simulated universes. A nearby superstructure could reveal its clusters, filaments, mass, and internal shape far more clearly than an extreme pattern near the edge of observation. It could show how a genuinely enormous section of the local web is assembled, and whether its scale agrees with the standard model. They showed that superclusters could join into structures extending across hundreds of millions, and then more than 1 billion light-years. The path toward the largest claimed structure therefore required a more careful example between the accepted walls and the far more controversial patterns. It required a superstructure large enough to dominate the nearby map, yet close enough for astronomers to examine its internal branches. And once the first great walls had shown how far the cosmic web could stretch, a newer map of the nearby universe would reveal an immense branching structure whose knotted form earned it the name Quipu. The name came from an ancient system of cords and knots once used in the Andes to store information. Quipu does not resemble one straight wall. It appears as a long central thread with smaller branches extending away from it, as though the surrounding clusters had been tied into a structure too large to see from any single point. Astronomers used galaxy clusters detected through their X-ray emission. Clusters contain enormous quantities of hot gas trapped by gravity. This gas reaches temperatures high enough to produce X-rays, allowing the clusters to stand out as some of the clearest markers of dense matter in the nearby universe. The approach does not reveal every filament or smaller galaxy group. It selects the heaviest landmarks, the regions where gravity has gathered enough material to create large clusters filled with hot gas. Quipu appeared within a survey designed to examine the matter distribution in the nearby universe. The researchers focused on a region extending from about 400 million to more than 800 million light-years away. The light from its clusters began traveling long before the earliest humans existed. Yet, compared with structures seen billions of light-years away, Quipu belongs to a part of the universe that can be mapped with far greater detail. The central spine is not a solid bridge. It is a chain of clusters and superclusters connected through a broader, overdense region. Between the bright knots lie galaxies, smaller groups, gas and dark matter. Wide gaps remain, but the overall density is higher than in the surrounding volume. Quipu contains dozens of rich galaxy clusters and many smaller systems. Its estimated mass reaches roughly 200 quadrillion times the mass of the Sun. Dark matter dominates the gravitational structure. Hot gas contributes more ordinary matter than all the stars combined, while the visible galaxies form only the most obvious lights inside the system. Its clusters, galaxies, and gas would no longer follow the gravitational framework that shaped them. It is a vast region where invisible mass has organized visible matter into a recognizable pattern. The Milky Way is roughly 100,000 light-years wide. More than 10,000 galaxies of that width could be placed end-to-end across Quipu's measured length. Its clusters appear in different directions, separated by empty-looking darkness. No glowing thread connects them for the human eye. The structure exists only after distances are measured and the three-dimensional distribution is reconstructed. Its identity comes from a pattern spread across more than 1 billion light-years. Some sections are denser than others. Some branches connect clearly to the central spine. Others fade gradually into the surrounding web. Astronomers identified Quipu through a method that links neighboring clusters when their separation falls below a chosen distance. One cluster is linked to a nearby cluster. That cluster may connect to another, and the chain continues until no additional members meet the selected condition. If the allowed separation is too small, one real structure may break into disconnected pieces. If it is too large, Separate systems may join into one artificial chain. Researchers therefore test different limits and compare the resulting structures with the surrounding density field. It belonged to a wider concentration of matter, containing a substantial fraction of the nearby cluster population. Together, these structures contained almost half of the galaxy clusters in the region, while occupying only a small fraction of its total space. Large parts of the surveyed universe contain relatively few rich clusters. A smaller set of connected regions holds a remarkable share of them. It demonstrates how much of the nearby universe's mass can gather inside a limited network of superstructures. Roughly a quarter of the matter in the surveyed volume may belong to the 5 most prominent systems identified in the analysis. The structures occupy only about 13% of the volume. The gravity of nearby superstructures changes the motions of galaxies. Those motions can influence measurements of cosmic expansion if they are not separated carefully from the broader flow. A galaxy moving toward a dense region may appear slightly closer or farther through its redshift than expansion alone would suggest. As ancient light crosses a changing gravitational landscape, it can gain or lose a tiny amount of energy. An enormous superstructure creates a broad gravitational region through which that light must pass. It does not produce a visible outline of Quipu in the microwave sky. At best, careful statistical analysis may find a subtle temperature effect consistent with what such a mass concentration should create. Quipu is strongly supported as a mapped concentration of clusters, but not every predicted influence can be isolated clearly from noise. Every mass concentration curves space-time, and a structure spread across hundreds of megaparsecs can create a broad lensing effect. Instead of one obvious magnified image, astronomers look for slight statistical changes across many background galaxies. They are not only objects being observed, they can alter the observations of everything behind them. A map of distant galaxies may carry small distortions caused by the local cosmic web. Measurements of expansion may include motions created by nearby mass. The sky cannot be interpreted as though the space between Earth and the distant universe were empty. The plane of our galaxy creates a zone where dust and stars make distant extragalactic objects harder to identify. A structure crossing this region can appear broken even when its unseen sections continue behind the galactic disk. X-ray cluster surveys help, because high-energy light can reveal massive systems through regions where visible maps become incomplete. Fainter clusters fall below detection limits. Low-mass groups may remain unrecorded. The branches of Quipu almost certainly contain more detail than the present map shows. One branch may extend farther than the current survey reveals. Another may turn out to connect less strongly than expected. Quipu was described as the largest known superstructure in the nearby universe and, within the study's framing, the largest reliably characterized cosmic structure of its kind. Some structures are reported to extend several billion light-years, but they are often based on much sparser traces and carry greater uncertainty. It is enormous enough to test the behavior of the cosmic web, yet close enough for many of its clusters to be studied individually. Astronomers can estimate their X-ray brightness, mass, position, and surrounding galaxy density. The internal shape can be compared with computer simulations. When similar methods are applied to simulated universes built from the standard cosmological model, structures with broadly comparable properties can appear. A structure more than 1 billion light-years long may seem too large for a universe expected to become smooth on great scales. But the simulation comparison suggests that its existence does not require new physics. The standard model can produce large, branching superstructures without making the entire universe uneven. Quipu is long, but it is not a solid block filling a 1 billion light-year cube. It is a narrow and irregular concentration embedded inside a much larger volume. Voids, lower density regions, and other structures surround it. When a sufficiently large region is averaged, Quipu becomes one fluctuation among many. The universe can contain a very long filamentary system, while remaining statistically homogeneous on scales larger than the structure. A coastline may contain one peninsula extending far into the sea. Its great length does not mean the whole continent follows that shape. A thin cloud can cross the entire sky without filling the atmosphere. Quipu can be immense in one direction while occupying only a modest fraction of the surrounding cosmic volume. Its form is extreme to human intuition, but not necessarily extreme to the mathematics of a vast universe. Humans evolved to understand distances measured in steps, journeys, and landscapes. Even the size of Earth exceeds direct experience. When a structure reaches that length, the first reaction is often that it should be impossible. How often should a feature like this appear in a universe of the observed size and age? If simulations produce similar structures often enough, then the apparent impossibility belongs to human scale rather than physical law. It is remarkable, but not clearly forbidden. A structure that agrees with the model can help reveal how large-scale matter affects precision measurements. It provides a nearby laboratory for studying the relationship between clusters, galaxies, dark matter, and surrounding filaments. A galaxy inside a dense superstructure may have experienced more interactions than one in the field. Gas can be removed as groups fall toward clusters. Star formation can decline in crowded regions. The study found enhanced galaxy density even outside the immediate superstructure regions, suggesting that the environment fades gradually rather than ending at a sharp edge. Its clusters do not float inside a separate container. They belong to a continuous density field whose effects weaken with distance. Named structures are useful, but their borders are human choices placed on a universe without clear dividing lines. Quipu may be compared with a knotted cord, yet no knot can be untied from the rest of the web. Its branches continue toward neighboring structures. Its voids connect with other voids. Gravity links its history to matter far beyond the catalogued members. Dense clusters may remain bound and continue merging internally. More distant branches may be carried apart by cosmic expansion. Its great length almost guarantees that no single gravitational center can gather every section together. Quipu is therefore a pattern of shared origin and present density, not one future galaxy or cluster waiting to form. Billions of years from now, observers inside one cluster might no longer see distant sections clearly. The structure could fade from view, even though its galaxies continue existing. Humanity can see enough of the nearby universe to connect the branches. Earlier civilizations on Earth lacked the instruments. Far future civilizations may lose the wider view as expansion carries distant galaxies away. Here is a structure longer than 1 billion light-years, mapped through dozens of massive cluster traces, tested against simulations, and found broadly compatible with standard cosmology. The Hercules Corona Borealis Great War may extend across several billion light-years, perhaps approaching 10 billion, according to some estimates. Unlike Quipu, it was not traced through a dense nearby map of galaxy clusters. Its possible outline emerged from a sparse distribution of brief, powerful explosions seen across the distant universe. Quipu can be examined as a branching superstructure with mapped members and an estimated mass. The Hercules Corona Borealis pattern is reconstructed from rare signals whose exact relation to the underlying galaxies remains uncertain. One structure shows how enormous the standard cosmic web can become. The other raises the possibility that the web contains a pattern so large that either the evidence is misleading or the expected limits of cosmic structure need to be reconsidered. Its length weakens the simple claim that every billion light-year structure must be impossible. Its agreement with simulations shows that gravity can create astonishing arrangements without breaking the broad smoothness of the universe. If one well-mapped structure can extend beyond 1 billion light-years, how far can a genuine concentration continue before it becomes too large to fit comfortably? within the same model. Its branches remain close enough, dense enough, and statistically ordinary enough to belong to the expected web. The far greater pattern in Hercules and Corona Borealis would be separated from it by scale, distance, age, and uncertainty. They would be trying to reconstruct an almost invisible wall from scattered flashes crossing a universe seen billions of years in the past. And beyond Quipu's well-mapped branches, the search would turn toward a far more distant pattern, whose possible size was so extreme that even calling it one structure became a serious scientific question. The suspected feature lies in the direction of the northern constellations Hercules and Corona Borealis, but it cannot be seen as a wall across the sky. There is no single image showing a bright structure with clear edges. No telescope has photographed its full shape, and no ordinary galaxy survey has traced every filament inside it. It appeared as an unusual concentration of distant events spread across a wide part of the sky and across a period of cosmic history when the universe was only a few billion years old. Quipu extends for roughly 1.3 billion light-years. The Sloan Great Wall reaches a similar order of size. The Hercules Corona Borealis pattern was initially estimated at around 2 to 3 gigaparsecs across. At the upper end of the estimate, light would require almost 10 billion years to travel from one side to the other. This does not mean the structure occupies 10 billion light-years of the universe as it appears today in a simple straight line. Cosmic expansion changes the relationship between distance, time, and redshift, especially so far into the past. A structure of that size would extend across a significant part of the observable cosmos. Its 100,000 light-year width could be repeated tens of thousands of times before reaching the other side. The events used to identify it were found around a redshift of roughly 2 in the earliest studies. The light began traveling when the universe was far younger than it is now, before the Sun or Earth existed. We are looking backward toward an ancient arrangement of matter. The galaxies connected with the pattern, if it is real, have continued evolving for billions of years since the light left them. Some have merged. Some have formed new stars. Their clusters may have grown, and their wider environment may no longer resemble the one reconstructed from ancient signals. Quipu can be studied through clusters whose positions and properties are mapped across a relatively limited distance. The Hercules Corona Borealis region is much farther away, where ordinary galaxies become faint and incomplete. The suspected wall may contain countless galaxies, but most are not individually included in the evidence that first revealed it. Those markers appeared more often in one broad direction and distance range than statistical smoothness seemed to predict. The concentration could mean that an enormous region contained more star-forming galaxies than average. It could mean that several smaller structures happened to lie close together in the same part of the sky. It could also mean that the sample was still too sparse to reveal the true shape. The Great Wall found in nearby redshift surveys was traced through thousands of galaxies. The Sloan Great Wall emerged from an even larger galactic map. Quipu was identified through many massive galaxy clusters. The Hercules Corona Borealis Great Wall was inferred from far fewer cosmic events. It describes the region across which the unusual concentration appears. Inside that region may be filaments, clusters, voids, and separate walls. The name joins them into one possible structure before their full connection has been demonstrated. Early maps of the nearby universe also began with limited data. The first large walls appeared before every galaxy inside them was measured. But the larger the claimed structure, the more dangerous an incomplete outline becomes. A few missing or misplaced points can alter the apparent boundary. A wider redshift range can stretch the estimated depth. A change in the statistical method can connect groups that previously appeared separate. They can shift the inferred size by distances larger than the Sloan Great Wall. The earliest analysis identified a strong concentration within a particular redshift interval. 14 of 31 measured events in that range appeared within roughly 1/8 of the sky. Different statistical tests suggested that the clustering was unlikely to be a simple accident. Later studies used larger samples and continued finding evidence for an unusual northern concentration. In some analyses, it became more prominent or appeared to extend across a wider range of distance. A random cluster created only by a small early sample might have weakened as the catalogue grew. Instead, later work continued finding something unusual in broadly the same region. The observations still do not show whether the events belong to one connected structure. A chain of separate walls could occupy the same direction while remaining divided by immense gaps. Several ridges may overlap in the line of sight and appear to form one continuous wall. Only better depth information reveals whether they belong together. For the Hercules Corona Borealis pattern, the haze is created by distance, limited samples, uncertain selection effects, and the rarity of the events being used. Once a pattern is called the largest structure in the universe, every new observation is viewed against that possibility. What remains uncertain is whether all of it should be treated as one wall. This distinction matters because cosmology does not forbid every long pattern. The cosmic web naturally forms filaments, sheets, and chains. A very long arrangement can occur if it is thin, irregular, or composed of several neighboring features. The more important question is how strongly the matter is connected, and how unusual the full concentration is compared with a universe built from the Standard Model. It requires a density pattern that stands out from the surrounding volume and remains significant under reasonable ways of measuring it. Quipu meets this requirement through a detailed nearby cluster map and comparisons with simulations. The Hercules Corona Borealis candidate has a more difficult burden because the claimed scale approaches the size at which the universe should appear broadly uniform. It allows clusters, voids, walls, and rare concentrations. It says that when a sufficiently large volume is examined, no direction or location should remain fundamentally special. A genuine wall approaching 10 billion light-years would make that averaging difficult. It would cover such a large region that finding enough independent volume around it becomes challenging. It would dominate a major part of it. If one region contains a coherent concentration of matter across several billion light-years, then either such structures are allowed more easily than expected, the transition to cosmic smoothness occurs on a larger scale, or the pattern has been interpreted too simply. The Standard Model has survived many earlier discoveries that initially sounded impossible. The CFA Great Wall appeared enormous when the surrounding map was small. The Sloan Great Wall seemed to challenge homogeneity before more careful analysis showed that its irregular shape and limited volume could fit within large simulations. Quipu extends beyond 1 billion light-years while remaining broadly compatible with the same cosmology. The Hercules Corona Borealis candidate is different mainly because the leap in scale is so large and the evidence so indirect. Its estimated length is several times greater than the largest well-mapped nearby superstructures. A structure this distant cannot be weighed through one clean method. Its galaxies are faint. Its filaments are difficult to trace. The light from its member systems has been stretched strongly toward redder wavelengths. Observations must also account for the fact that the universe at that time was forming stars more rapidly than it does now. The rare events used as markers may not follow ordinary matter perfectly. They may prefer certain kinds of galaxies, chemical environments, or stages of stellar evolution. A region rich in those conditions could produce more markers without containing an equally dramatic excess of total mass. Astronomers need information about the galaxies hosting them, the surrounding galaxy density, and the possible observational biases affecting which events receive measured distances. Satellites have different fields of view. Ground-based telescopes follow some afterglows more successfully than others. Dust in the Milky Way can make optical measurements harder in certain regions. An explosion must occur with a beam directed toward Earth. A satellite must detect it. Observers must locate its fading afterglow. A telescope must measure a spectrum or identify a host galaxy well enough to determine redshift. Researchers test these effects and have argued that known biases do not fully explain the Hercules Corona Borealis concentration. The safest description is that a statistically unusual clustering has been found in a region associated with Hercules and Corona Borealis. To accept it as one wall, astronomy must connect those flashes to the matter between them. That matter may occupy an ancient landscape containing hundreds of thousands or millions of galaxies. Each one may last seconds, while the structure they are used to trace spans distances light crosses over billions of years. A momentary burst becomes a marker for an object older and larger than almost anything the mind can picture. The entire wall may have been inferred because a small number of dying stars happened to send their narrow beams towards Earth. If their jets had pointed elsewhere, the pattern would be invisible to us. The structure, if real, would not change. Only our ability to notice it would disappear. This is why the discovery feels both powerful and fragile. Gamma-ray bursts can be seen across enormous distances, farther than most ordinary galaxies can be mapped in detail. They open a path into regions of cosmic history that other tracers cannot reach easily. But they are rare. A sparse tracer can reveal an immense structure long before enough ordinary galaxies are observed to confirm it. It can also create patterns that remain ambiguous for decades. The Hercules Corona Borealis Great Wall sits inside that ambiguity. It may be one extraordinary feature of the cosmic web. It may be a collection of neighboring structures seen at limited resolution. It may be partly shaped by how the events were detected and how their distances were measured. The data do not yet allow the possibilities to be separated completely. More recent analyses have suggested that the northern concentration may extend over an even wider range of redshifts than the earliest definition. If that extension is physical, the possible feature becomes larger and more complicated. If it combines different structures across time and distance, the idea of one wall becomes harder to defend. A broader pattern can strengthen the evidence for unusual clustering while weakening the claim that the clustering belongs to one object. This tension is central. More data do not always make the answer simpler. They can reveal that the original boundary was too narrow, but they can also show that the structure has no clean boundary at all. The cosmic web may contain a broad northern region, rich in massive star formation and large-scale matter concentrations, without forming one continuous wall. Or, the available points may be the first visible markers of something genuinely enormous. Only a denser map can decide. Future missions capable of detecting many more distant bursts and measuring their redshifts more uniformly could transform the picture. Large infrared and optical surveys may also map the host galaxies and surrounding matter more directly. The wall may eventually break into several known structures. It may shrink, it may grow, or it may remain a statistical feature without a complete physical outline. For now, its possible size places it beyond Quipu, the Sloan Great Wall, and every nearby superstructure that can be mapped in detail. But the record comes with an asterisk larger than the record itself. The largest claimed structure in the universe may be real, yet it has not been observed in the same way as the structures that came before it. Its existence depends on whether brief explosions can serve as reliable lights placed along an otherwise invisible cosmic landscape. And to understand why a handful of distant flashes could reveal a wall billions of light years across, the search had to follow the gamma-ray bursts themselves, from the deaths of massive stars to the narrow beams that crossed the universe and reached Earth. For a few seconds, it can release more high-energy radiation than the sun will produce across most of its entire life. The burst may arrive without warning from a point that appeared completely dark before the event began. What remains is an afterglow, a weakening signal that can be followed through X-rays, visible light, infrared, and radio waves. The explosion itself is brief, but the information carried by its light can reveal a distant galaxy, a dying star, and the large-scale environment in which the event occurred. Some last only a fraction of a second and are linked to the mergers of compact objects, such as neutron stars. Others continue for several seconds or longer, and are usually associated with the collapse of very massive stars. The bursts used to trace the possible Hercules Corona Borealis Great Wall are mainly important because many long-duration events can be detected across extraordinary distances. Near the end of its life, the core can no longer support the weight above it. The center collapses, while the outer layers begin taking part in a violent stellar death. In certain cases, the collapsing core forms a black hole or an extremely compact neutron star surrounded by rapidly moving material. These jets travel outward at speeds close to that of light, piercing through the dying star and carrying intense gamma radiation into space. Most of it is concentrated into two narrow beams extending from opposite sides of the star. Earth detects the event as a gamma-ray burst only if one of those beams happens to point toward us. Their explosions still occur. Their host galaxies still contain the same kinds of stars, but from our viewpoint, they do not appear as gamma-ray bursts. A narrow beam can be seen from billions of light-years away, while an equally powerful explosion pointed in another direction remains almost invisible. When one reaches Earth, the signal may first be detected by a satellite designed to watch large areas of the sky. Gamma rays do not pass easily through the atmosphere, so the initial flash must be observed from space. The satellite measures the direction as quickly as possible and sends an alert to telescopes around the world. Within minutes or hours, ground-based observatories may turn toward the position and search for visible or infrared light. X-ray and radio telescopes follow the same fading source at different wavelengths. A bright afterglow may reveal absorption lines from gas along the path. A spectrum can show how strongly the light has been shifted toward longer wavelengths. Satellites have detected many gamma-ray bursts, but only a fraction receive reliable redshift measurements. Some lie behind dust that hides visible light. Others occur in regions of the sky that are difficult to follow from the ground at the right time. The events available for large-scale structure studies are therefore not a complete record of every burst. If these losses occurred equally across the sky, the remaining sample would still be useful, though sparse. Satellites may spend more time viewing some regions than others. The Sun, Moon, and Earth can block parts of the sky. Ground-based telescopes have seasonal limits. Weather interrupts follow-up observations. Researchers must separate real cosmic clustering from the uneven way the sky was observed. Every astronomical survey has selection effects. A galaxy survey misses objects below its brightness limit. A radio survey depends on wavelength and sensitivity. An X-ray cluster catalog favors systems filled with hot gas. If a catalog contains millions of galaxies, modest observational differences can often be measured and corrected statistically. If a distance interval contains only a few dozen gamma-ray bursts, the location of each event matters greatly. Moving or removing a small number of points can change the apparent significance of a concentration. This is why the Hercules Corona Borealis pattern cannot be treated like a nearby wall drawn by thousands of galaxies. Massive stars live briefly, so they explode close to the places where they were born. A region producing many new stars may therefore create more long-duration bursts than an equally massive region filled mainly with older stars. The early universe formed stars more rapidly than the modern universe, and distant galaxies often differed from nearby ones in size, composition, and internal structure. Many long bursts appear to prefer galaxies with relatively low amounts of heavy elements, although the relationship is not absolute. A region containing many suitable young galaxies could produce an excess of bursts, even if its total matter density were only moderately high. It may also indicate a concentration of the environments that produce gamma-ray bursts efficiently. If an enormous structure contains more galaxies, it should generally contain more massive stars and more bursts. A quiet cluster filled with old galaxies may contain tremendous matter while producing few long gamma-ray bursts. The flashes illuminate where certain stars are dying, not where every kilogram of matter is located. Ordinary galaxies become difficult to study individually across the deepest reaches of the observable universe. Their light spreads out, shifts towards infrared wavelengths, and can fall below survey limits. The narrow jet concentrates enough energy for the event to remain detectable when the galaxy itself would be a faint smudge or completely absent from a shallower survey. The spectrum may reveal not only the burst's distance, but also material along the path. This is why gamma-ray bursts can hint at structures long before ordinary galaxy maps become dense enough to confirm them. When several appear close together in angle and distance, astronomers ask whether they are marking the same overdense region. The question is statistical, because the space between them remains mostly unobserved. If many flashes occur along the same broad horizon, they may reveal a mountain range. But without steady light, it is difficult to know whether the peaks belong to one continuous ridge or several separated ranges aligned in the same direction. The Hercules Corona Borealis Great Wall is the possible landscape inferred between the flashes. The original concentration became noticeable because an unexpectedly large fraction of bursts within a certain redshift range occupied a relatively small part of the sky. They compared angular separations between bursts. They divided the sky into regions and counted how many events appeared in each one. They used nearest neighbor methods and other statistical tools to ask how likely the distribution would be if the events were placed randomly. A test can show that points cluster more than expected without revealing what connects them. Researchers revisited the northern concentration and found that unusual clustering continued to appear. This persistence strengthened the case that the original pattern was not created by one accidental grouping. Different analysis could identify somewhat different centers, boundaries, and scales. It may also be showing that the original wall was an artificial boundary placed on a broad and complicated distribution. The more the pattern spreads, the harder it becomes to describe as one clean structure. Walls curve and branch, filaments intersect, voids interrupt dense regions. Separate superclusters can lie near one another without belonging to one bound system. A distant, sparse catalog may compress all of this complexity into one broad concentration. The name Great Wall may survive because it is memorable, even if the final map turns out to contain several structures. A constellation looks like one pattern because stars at different distances are projected onto the same sky. The shape is real as an appearance from Earth, but its stars may have no physical relationship. The Hercules Corona Borealis concentration includes distance information, so it is more than a simple angular alignment. Yet the redshift range is still broad enough for separate structures to overlap within it. A redshift can be measured precisely, but translating it into a present-day separation depends on the cosmological model and on how expansion is described. The distance between two ancient events when their light was emitted is not the same as the separation their descendant galaxies would have today. A figure of 10 billion light-years may refer to an estimated co-moving extent, a way of describing distance while accounting for cosmic expansion. Its separate regions are seen at different moments, through light released billions of years ago. The farther the points are from one another, the greater the challenge of treating them as parts of one simultaneous object. The question is not whether a giant barrier stands between Earth and the edge of the universe. The question is whether matter and star-forming galaxies were distributed unevenly across a region several billion light-years wide. If the answer is yes, then cosmologists must decide whether the unevenness is allowed by the Standard Model. A confirmed giant structure would change the scale at which the cosmic web must be understood. A divided structure would reveal the limits of sparse traces and the danger of turning statistical groupings into single objects. An observational bias would reveal how easily the instruments and follow-up process can shape a cosmic map. The photons passed through expanding space, becoming redder and weaker, until a detector near Earth recorded the sudden arrival. A satellite received the signal, computers measured its position, and telescopes searched for the fading afterglow. From that chain of observations, astronomers assigned one more point to the three-dimensional universe. A detector records energy. A telescope measures a spectrum. A catalog gathers positions. Statistics reveal an unexpected concentration. If the analysis creates a convincing pattern from biased data, a wall may appear where no single structure exists. A larger sample would reduce the influence of individual points. Uniform sky coverage would make angular comparisons safer. More redshifts would fill the distance range. Fast communication between satellites and ground observatories could increase the fraction receiving reliable distances. Infrared telescopes could follow afterglows hidden by dust or shifted beyond visible wavelengths. If the events truly trace one immense overdensity, the host galaxies and surrounding matter should reveal related structure. If the wall breaks into smaller pieces, those surveys may show separate concentrations divided by large gaps. A structure several billion light-years across cannot be photographed from the outside. Its map will remain a reconstruction. But the reconstruction can become dense enough to show whether the name wall is physically useful. Until that happens, gamma-ray bursts remain both the strongest evidence and the greatest source of uncertainty. This balance explains why the Hercules Corona Borealis Great Wall has remained famous without becoming fully accepted as one confirmed object. If the bursts trace one connected cosmic overdensity, the scale may approach 10 billion light-years. If they trace several separate structures, the record belongs to an appearance created by limited resolution. If selection effects contribute strongly, even the apparent concentration may change as observations become more uniform. That interpretation matters because the possible wall touches one of the deepest assumptions used to describe the cosmos. The Standard Model allows irregularity, but expects those irregularities to average out across sufficiently large volumes. A genuine structure of several billion light-years would not simply be another large item in a catalogue. It would force astronomers to examine where cosmic smoothness begins and whether the early universe could naturally produce such a dominant pattern. That question belongs to the comparison between the claimed wall and the cosmological principle. And once the distant explosions had drawn the possible outline of the wall, the unsettling problem was no longer how it had been detected, but whether a universe expected to become smooth could contain a coherent structure on such an enormous scale. When the universe is viewed across a sufficiently large volume, matter should be distributed in roughly the same way everywhere. No direction should remain permanently richer than another, and no location should occupy a uniquely important position. On smaller scales, it is deeply uneven. Stars gather into galaxies. Galaxies gather into groups and clusters. Clusters connect through filaments, while enormous voids open between them. A map covering a few 100 million light-years may be dominated by one dense wall or one vast empty region. But as the map expands, more walls, voids, and clusters enter the picture. Their differences should begin averaging together. This broad assumption is often called the cosmological principle. It allows astronomers to describe the universe through average density, average expansion, and large-scale geometry, rather than calculating the influence of every galaxy separately. Every direction could require a different history. Every region could expand according to its own rules. Measurements made from Earth might reveal only a local environment with no connection to the wider universe. The success of modern cosmology depends partly on the idea that Earth is not observing from a special place. The cosmic microwave background strongly supports this picture. Its ancient glow is almost the same temperature in every direction, with only tiny variations carrying the seeds of later structure. Large galaxy surveys also move toward a more even distribution as the sampled volume increases. Astronomers sometimes call it the scale of homogeneity, the distance across which local clumps and voids begin blending into a stable cosmic average. A structure does not suddenly become forbidden because it crosses one exact line. Different measurements, tracers, and statistical methods can produce somewhat different estimates. A smaller region can be strongly uneven. A larger one becomes less uneven. Eventually, the remaining differences should be modest enough that the universe can be treated as homogeneous for broad calculations. Cosmology does not contain a simple rule stating that no wall may exceed a particular length. A structure can be extremely long and still occupy only a narrow part of a much larger volume. It can contain gaps, branches, and separate concentrations while remaining statistically compatible with the broader universe. A thin filament crossing 1 billion light-years may add less mass to the surrounding volume than a shorter but much denser concentration. A chain of several superclusters can look like one enormous wall without behaving as one coherent system. To judge whether a structure truly creates a problem, astronomers must examine its density, shape, volume, internal connection, and probability. The Hercules Corona Borealis candidate is especially difficult because the evidence does not reveal a continuous field of galaxies between the distant bursts. The proposed wall may contain many smaller structures whose edges happen to overlap in a sparse map. The largest distance between two markers would then describe the reach of a pattern, not the size of one physical object. Several ordinary structures spread across a broad region are not the same as one extraordinary structure filling that region. But if future surveys reveal a connected concentration extending across several billion light-years, the problem becomes harder to dismiss. A genuine overdensity on that scale would remain visible even after a very large volume was averaged. It could imply that the transition toward cosmic smoothness occurs farther out than expected. Those fluctuations would have needed to grow into a structure much larger than the best-mapped walls seen nearby. Even if a structure has a very small chance of appearing in one region, it may still appear somewhere inside the observable volume. This is why the existence of one surprising feature does not immediately overthrow the model. Researchers begin with early conditions consistent with the cosmic microwave background, then allow dark matter, ordinary matter, gravity, and expansion to evolve. Astronomers can search these artificial universes using the same methods applied to real observations. They can ask how often a structure resembling Quipu appears, how long the largest wall becomes, and whether rare alignments can imitate something far larger. If the simulated box is only slightly larger than the structure being tested, it cannot contain enough independent regions to estimate rarity properly. A search algorithm that connects neighboring points can produce longer structures when the chosen linking distance increases. A method that smooths the density field can merge nearby concentrations into one feature. The same simulated universe may contain different largest structures depending on the way the map is analyzed. Nature provides a continuous distribution of matter. Humans choose how to divide it into walls, filaments, clusters, and superclusters. A different method may decide that one giant wall is better described as 3 related superstructures. For the Hercules Corona Borealis region, sparse gamma-ray bursts leave far more room for interpretation. A statistical concentration may be robust even when its exact physical shape remains unknown. The universe may genuinely contain more distant star-forming regions in that direction than average. A galaxy cluster is coherent because its members are bound strongly enough to remain associated. A supercluster can be coherent only as a pattern. Its separate regions may never collapse toward one center. A structure billions of light-years across would almost certainly belong to this final category. The time required for light or gravitational influence to cross the full length might approach a large fraction of cosmic history. The earliest density fluctuations were not isolated points. They followed patterns across many scales. Gravity acting locally on those patterns could produce aligned structures, without every section communicating directly. A wall can therefore be coherent in appearance and origin, while remaining disconnected in its later motion. The structure does not need gravity to pull its entire length together after the universe began. It only needs the early matter distribution and later local growth to create a related pattern across the region. But the standard early fluctuations still place limits on how strong those relationships should become. If a future map showed one dense continuous wall spanning close to 10 billion light-years, the expected statistics would be placed under real pressure. The problem would not be that gravity worked too slowly to build it from one side to the other. The problem would be that the early universe should not have contained such a large and strong imbalance, according to the simplest version of the model. Distances may be correct individually while the boundaries of the wall are too broad. Some bursts may belong to unrelated structures. The selection of the redshift range may exaggerate the depth. Gamma-ray bursts may concentrate more strongly than matter because they favor certain young galaxies and stellar environments. The structure could lie near the extreme edge of what the model predicts, without falling beyond it. Extraordinary observations often become less mysterious when measurements improve. Sometimes, the object shrinks. Sometimes it separates into several pieces. Sometimes the model turns out to allow more variation than an early estimate suggested. Repeated observations strengthen the anomaly. Independent methods find the same effect. Simulations fail to reproduce it without changing the assumptions. If the Hercules Corona Borealis pattern survived every test as one connected overdensity, cosmologists might need to reconsider the initial conditions, the growth of structure, or the scale at which homogeneity is reached. A parameter could shift, a statistical estimate could broaden. The early spectrum of density variations could require refinement. Some models introduce features beyond the simplest cosmological picture, such as unusual conditions during inflation, non-standard behavior of dark matter, or large-scale effects not fully captured by present simulations. They belong to the questions that would follow only after the structure became firmly established. This makes the possible wall less useful as proof against cosmology, but highly useful as a test of how cosmic structures are identified. It exposes the difference between a collection of points and the matter field beneath them. It shows how record-sized claims depend on survey design, distance measurements, statistical choices, and the behavior of the tracer. Its walls blend into filaments. Its filaments meet clusters. Its clusters sit beside voids. Boundaries fade rather than stop. At the greatest scales, the universe may offer only patterns whose edges depend on how closely we choose to look. The title remains appropriate because the possible scale is difficult to reconcile with the simplest mental picture of cosmic smoothness. There is an unusual distribution of distant explosions that may trace something enormous. The difference between those statements is the space where the science remains unfinished. If the warn is confirmed, the cosmic web may contain coherent patterns on scales far greater than well-mapped nearby structures. If it separates into smaller systems, it will show how limited data can merge different pieces of the universe into one apparent object. If the burst distribution reflects stellar environments rather than total mass, it will reveal how strongly the chosen tracer shapes the map. A wall can exist statistically, visually, and historically without existing as one gravitational object. It can be composed of real overdensities whose relationship depends on the scale of observation. The universe may not provide a final answer to where one structure ends and the next begins. The closer astronomy moves toward the larger scales, the more difficult those categories become. If the wider universe is much larger than the visible part, rare structures have even more opportunities to appear somewhere. The largest known structure may therefore be partly a result of where humanity happens to stand and which part of the total cosmos can be seen. The universe can be statistically uniform, while each observer sees a different set of extremes. It means no observer occupies a fundamentally privileged location when enough volume is considered. The Hercules Corona Borealis candidate may be one rare extreme inside that broader equality. The galaxies between the bursts must be measured. Their density, redshift, star formation, and connection to surrounding structures must be reconstructed. Gravitational lensing may reveal mass that does not shine. Infrared surveys may uncover distant galaxies hidden from visible light. If the wall exists only in gamma-ray bursts, its physical interpretation will remain uncertain. If several independent maps reveal the same broad overdensity, the claim will become much stronger. A structure billions of light-years wide cannot be confirmed through one observation or one telescope. It requires years of catalogues, overlapping surveys, and statistical tests that repeatedly ask whether the same pattern remains. It may transform into a network of smaller structures whose combined extent remains astonishing even after the single-wall interpretation is abandoned. The Great Wall changed as larger surveys placed it in context. The Sloan Great Wall became more complex when its internal superclusters were studied. Quipu gained meaning through comparisons with simulations rather than through length alone. The Hercules Corona Borealis pattern will also need context before it can become more than a possible record. That context may finally show that the universe can create structures far larger than expected. And once the possible wall had been measured against the expected smoothness of the universe, the final question became whether astronomy had discovered one impossible structure, several ordinary structures aligned across the same region, or a pattern created partly by the way we observe the distant cosmos. It may emerge slowly. As more distant galaxies are measured, more gamma-ray bursts receive reliable redshifts, and different maps begin to overlap across the same ancient region of space. If the Hercules Corona Borealis concentration is one enormous structure, the matter between the known events should leave additional evidence. Galaxies should gather more densely across part of the region. Clusters should appear where several filaments meet. Gravitational lensing should reveal mass even where ordinary light remains faint. A structure appearing independently in galaxies, clusters, gas, lensing, and stellar activity would be much harder to dismiss. The distant universe is gradually becoming more accessible to this kind of comparison. Large telescopes can observe galaxies whose visible light has been stretched into the infrared. Wide surveys can cover immense areas of sky, while recording more objects than earlier astronomers could have studied across an entire career. Spectroscopic instruments can measure many galaxies at once, turning faint points into positions inside a three-dimensional map. A photograph can show thousands of galaxies, but distance measurements are needed before their true arrangement becomes clear. Without depth, foreground and background systems overlap on the same sky. The wall can only be tested when enough of those layers are separated. The final map could reveal a broad chain of superclusters connected through weaker filaments with large voids interrupting the pattern. Some sections may belong together naturally, while others may only appear related because the cosmic web continues beyond the boundaries chosen by the survey. The gamma-ray bursts may have identified a genuinely unusual region, while the name Great Wall simplified its internal structure. A bright point becomes a binary star. A smooth galaxy becomes a system of arms, streams, dust lanes, and dark matter. A single supercluster becomes a network of smaller flows. It could separate into several enormous structures that happen to occupy a related area of the early universe. Each part might be entirely compatible with the standard model, while their combined appearance creates the impression of something almost impossible. But it changes the meaning of the title. One coherent wall, several billion light-years wide, would challenge the expected scale of cosmic smoothness. Several independent structures spread across that distance would show how easily the eye and the statistic can join separate parts of the web into one pattern. Only one places serious pressure on the basic cosmological picture. The unusual concentration may be real, but gamma-ray bursts may exaggerate it because they prefer particular kinds of galaxies. A distant region with unusually intense star formation could produce many massive stars and therefore more long-duration bursts. The total matter density might be elevated only modestly, while the number of explosions rises much more strongly. In that case, the map would reveal not the largest structure in total mass, but one of the largest known regions rich in the conditions that create certain stellar deaths. It would suggest that galaxy evolution itself varied across an enormous part of the early universe. If they share unusual properties, such as rapid star formation or low heavy element content, the burst concentration may reflect environment more than mass. If ordinary galaxies and clusters are also unusually common in the same volume, the case for a true large-scale overdensity would become stronger. Each new generation of instruments can examine deeper light and separate objects that earlier surveys blended together. What now appears as darkness between the bursts may gradually fill with galaxies. Or it may remain empty enough to divide the candidate wall into smaller sections. The larger structure may become smaller, or it may lose the status of one structure altogether. The claim sits close to the boundary between what the standard model comfortably allows and what would require a deeper explanation. Testing that boundary reveals how well astronomers understand structure formation, survey bias, cosmic statistics, and the meaning of homogeneity. If the wall dissolves because sparse traces created a misleading connection, future studies will know how easily the same effect can appear elsewhere. If selection bias produced part of the concentration, gamma-ray burst catalogs can be corrected more carefully before they are used to map the distant universe. If the structure separates into several walls, astronomers will gain a better picture of how the early cosmic web was assembled. Suppose future galaxy surveys reveal a broad overdensity across the same region. Suppose independent tracers confirm that the concentration extends for several billion light-years. Suppose simulations using standard early conditions rarely or never produce anything comparable. It would become evidence that some part of the cosmological model is incomplete. The model already explains the expansion of the universe, the cosmic microwave background, the growth of galaxies, and much of the large-scale web with remarkable success. A single anomaly would need to be understood beside all of those achievements. The universe may become broadly smooth, while still allowing rare structures larger than earlier estimates suggested. An ocean can have a stable average depth while containing trenches and mountains far from that average. A planet can have an ordinary climate while producing rare storms of extraordinary size. The cosmic web may permit exceptional regions without losing its broad uniformity. A structure identified through gamma-ray bursts should be searched for in simulations using gamma-ray burst-like traces, not only through the total matter field. Observational gaps, redshift limits, and uneven sky coverage should be reproduced as closely as possible. The apparent tension may come partly from the difference between the two methods. The universe is never observed directly as a complete three-dimensional object. Every map is filtered. Visible light surveys select bright galaxies. X-ray surveys select hot gas and massive clusters. Radio observations reveal different forms of matter. Gamma-ray burst catalogs select rare explosions whose jets happen to point toward Earth. The larger picture appears only when those versions are combined. There are regions too distant for their present light to reach us. There are galaxies hidden by dust, objects below detection limits, and structures beyond the observable horizon that can never enter our maps. The largest known structure is therefore not necessarily the largest structure that exists. It is the largest candidate humanity has been able to identify within the visible universe, using the available traces and definitions. Or the Hercules Corona Borealis pattern may already represent an extreme that would remain rare across a universe far larger than the observable region. From Earth, the web is reconstructed outward in every direction. From a galaxy billions of light years away, the map would be centered somewhere else. Its largest known structure might have another name and another shape. The largest structure becomes partly a property of the visible volume around each observer. The galaxies, clusters, and bursts are real. But which structure becomes the largest known example depends on the region that can be observed and the method used to divide the web into features. The record is always local to knowledge, even when the scale is cosmic. This makes the title less like a final answer and more like a doorway. The largest structure in the universe should not be possible only if it is truly one coherent overdensity, if its size has been estimated correctly, if the traces follow matter reliably, and if the expected statistics of the standard model have been applied fairly. Each condition remains open to investigation. Remove one of them, and the contradiction may disappear. Confirm all of them, and the contradiction becomes difficult to avoid. For now, the wall remains suspended between those outcomes. It is neither a confirmed failure of cosmology nor a meaningless accident. It is an unresolved pattern large enough to test the limits of the map. That may be the most honest place to leave it. The universe has repeatedly shown structures that seemed too large when first discovered. Wider surveys placed some of them into context. Better simulations showed that rare walls could arise naturally. New methods divided single features into more complicated systems. But each time the map expanded, the sense of scale changed again. The Milky Way became one point inside the local group. The local group became a small part of Laniakea. Laniakea became one concentration inside the cosmic web. Great walls crossed regions far larger than superclusters, and Quipu revealed a branching structure more than 1 billion light-years long. Then, the gamma-ray bursts pointed towards something several times greater. Whether that final pattern is one structure or many, the path toward it reveals a universe organized across scales that human intuition was never built to understand. The cosmic web is not a background decoration around galaxies. It is the architecture that gave galaxies their locations, guided their growth, and separated them with voids wide enough to contain entire histories of light. Its largest features are not solid objects waiting to be visited. They are distributions of matter, motion, and time, reconstructed from signals that reach Earth after traveling for billions of years. No spacecraft could cross them. No observer could stand outside them. A civilization could live inside one branch for its entire existence without ever seeing the full structure to which its galaxy belonged. Humanity may already live inside such a hidden arrangement on a smaller scale. We know our place only because telescopes allow us to combine light from many directions and many eras. The same instruments that make the universe visible also remind us how incomplete the view remains. A gamma-ray burst appears for seconds. Its light may have traveled for most of the age of the universe. Astronomers record the flash and place one point on a map. Another burst adds another point. Years of observation slowly create a pattern that may extend farther than light could travel during most of cosmic history. This is how the possible largest structure enters human knowledge, not as a wall seen all at once, but as a faint relationship between rare moments. The structure may eventually be confirmed. It may divide into smaller walls. It may fade into a statistical effect produced partly by the way distant explosions are observed. None of these endings would make the journey smaller. The real discovery is that the universe can hide its greatest architecture in patterns too large for any single image and too old for any direct view. From Earth, the night sky still appears calm. The Milky Way still crosses the darkness as a pale band of light. The stars do not reveal the filaments beyond them, the vast voids surrounding distant clusters, or the possible wall reaching across billions of light years. Yet, beyond that familiar sky, matter forms structures so immense that galaxies become almost invisible inside them. The largest may still be waiting for confirmation. It may still be waiting for a better name. And it may never provide the clean boundary that human language expects. What remains is the quiet possibility that the universe is both smoother and stranger than it first appears, uniform in the average, and filled with rare patterns capable of stretching across a significant part of everything we can see. Thank you for spending this time with Just About Space. If you enjoyed this calm journey through the cosmic web, subscribe for more documentaries about the hidden structures and distant mysteries of the universe. And wherever you are watching from tonight, take one more look at the darkness beyond the stars. The greatest structure we have ever found may not be a wall at all, but a question still spreading across the universe. Good night.